Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge. Successful pairs of spells and potions. So what the problem says is we get two positive integers, two positive integer arrays. One is spells and one is potions, and each of them has a different length. And spells represents the strength of a spell, and potion basically represents the strength of a potion, right? And we have this integer success that is passed as an input, and we call a pair of a spell and potion successful if the product, so spell multiplied by potion, is bigger or equal to this success value, right? And what we want to do is return an array of pairs that it has the same length as spells, where the value of pairs is the number of potions that will form a successful pair with the spell at index I. So the pairs at index I will contain the number of potions that can be paired with the ith spell and give us a successful pair, which basically means that the product will be bigger or equal to success. So that's the idea. If we take a look at this first example here, we have these spells and then these potions, right? And so for 5, we can create a successful potion with 10, right? 5 multiplied by 10, that's 50, bigger than 7. 5 multiplied by 2, so 2, it works, that gives us 10, bigger than 7. 5 with 3, that works as well. 5 with 4 works. 5 with 5 works. So it works with all of these. So we have 4 successful pairs. With 1, it doesn't really work with any of them. The biggest one you can multiply it with is 5, which still make it smaller than success. So for 1, it's 0. For 3, well, it works with 3 multiplied by 3, multiplied by 4, and multiplied by 5. So we have 3 pairs. So that's what we have here. So that's sort of the idea. Now how do we solve it? Okay, so how do we tackle this? Well, the problem says that what we are looking for is pairs with, so for each spell I, right? What we are looking for is all the products, right? All the potions that we can pair it with, such that, so all the, let's call it J potion, such that what we have is S of I, so the strength of the spell at index I, multiplied by the pair potion that we are pairing it with. Let's call P the strength of the potion. This needs to be bigger or equal to success, right? We can definitely do this in a brute force way, right? So we can just iterate over S, right? And then iterate over the indices in P, and then just check if basically this formula here is valid. Then we can just increment the number of pairs for I. Right? So that would be straightforward, but that would be O of the length of S multiplied by the length of P. Okay, and both of these can go up to 10 to the power of 5, so that's not a good solution. And so where can we optimize this? The first part that will be really tricky to optimize is this for loop, because we need it for each pair, because for each spell we want to get all the potions that can be paired with it. So this one will be tricky to optimize, but can we optimize this one? And the answer is yes, because if you look at this here, if you look at this function, what property does it have, this function here? Well, one property is that if this is true, if we fix Si, so for a specific spell, if it's true for PG, then this means that S of I multiplied by PG plus 1 will be bigger or equal to success. If we sort P, so if we sort P, right, the potions, then we guarantee that this value is going to be bigger or equal to success, because we multiplied by smaller value. So if we multiply by bigger value, the overall number will be bigger. And so if the smaller number was bigger or equal, then the bigger number will also be bigger or equal, right? And so if we sort P, then we guarantee that all the indices after J will work, right? And so what this means is that we can just use binary search, right? After sorting P, we can just use binary search to find the first index J that has this function valid, right? And once we have that index J, then we know that, let's say this is J where 1, 2, 3, 4, 5. So for example, for S of I equal, so this would be P. So for S of I equal to, let's say 3, our success is equal to 7, right? We just need to find the first value in this P that will make it, multiplied by 3, will make it bigger or equal to 7. What's that first value? It's not 2, because 2 multiplied by 3 is 6, but it's 3. 3 multiplied by 3, 9, bigger than 7. And so we don't need to go check the other values. We don't need to. We know that because this is sorted, then all of the remaining values will work fine. And so all we need to do is just get this index, which is 2, and then say the number of pairs is actually just the length of the array, which is 5, right, minus the index, which is 2, equal to 3. So we know we have 3 pairs. Okay, and so now basically we reduced our problem to just binary searching, right? So now our problem is just binary search. First index in P, so we will sort P first, and then we can just binary search for the first index in P. That gives us, for a specific, we will keep this loop, so we'll keep this loop, but that it gives us that S of I, so I from here, multiplied by that index, right, bigger or equal to success. So this is what we'll binary search with. Okay, so now what's remaining is just applying this binary search template to this, right? So with binary search, what we need is to find some sort of pattern where a function is false, starts out as false, and then continue being true, right? I'm going to do the full binary search. If you want to do it quicker, you can use just bisect with Python, and that should be a quicker solution. But I think it's good to practice binary search here. So what are we looking for? We are looking for the first true value, this position here, right? That has this function. So what is our function here? Well, what's the variable? The variable is this index, right, for P. This is the variable. This is the thing that changed. And this is the thing where as you increase the indices of P, if it was true for, let's say, index 2, like here, we know that it will be true for 3 and 4. For future indices, it will be true, right? And so here, our function is going to be just, let's call it f of x. It's going to be s of I. S of I is already fixed because we do the external for loop, multiplied by p of x. So this is the index that we get passed to the function, is bigger or equal to success. This is going to be our binary search function. And now we just need to put low and high in the boundaries and do the normal binary search, right? And so low is going to be the starting index of the P array. So we go just beyond the boundaries so that we guarantee that we don't make a mistake. So we put -1 here, and for high we'll go all the way to the end of the array. So it's just the length of P. Okay, and now we just move our pointers here for low and high such that f of low is always false and f of high is always true. Those are just the invariant of binary search. And when do we stop? Well, we stop when high is here and low is here, which means basically we keep going as long as high minus low is bigger than 1, right? Once the difference is 1, we stop and we return this index for our result, and we use this index to do the length of P minus the index, which will be at high value, right? Because this is the f of I. So just normal binary search here. So that's the idea. We will do a loop for I, but instead of doing this loop for J, we'll just binary search, right? We'll binary search for the first index P that has this function valid. Let's call it index, and then the pairs of I is just going to be equal to the length of P minus this index, right? Because that's what this means here. And what's the time complexity? And of course we will sort before doing all of this. Now what's the time complexity of this solution? Well, this is O of n being the length of S, and this binary search is O of log n, or let's call it NP, because it's the length of P. And so overall we have O of n log NP, right? And this should be efficient. Yeah, so that's pretty much the idea. Instead of doing brute force, you do one loop for the values of the spell, and then you binary search for the values of potion. Now let's implement this and make sure it passes. Okay, so let's implement this solution. So first, I'm just going to change the names here so that's easy to write. And then first we want to sort potion, right? Because we will binary search on it. And what we need is the length of both, right? Just to make this easier. So the length of spells and the length of potions. And then we need also the pairs, right? So let's just have an array for pairs that we return at the end. And now we go through the spell values, right? So let's call it S in spell. And now we do our binary search, right? For the first index, right? In P, such that S multiplied by that P of index is bigger or equal to success. That's what we are looking for. And so to do that, well, we just do our binary search. So the boundaries are first outside of the range, we are just outside of the range we are searching in, so that we don't run into any issues if, let's say, all the array has values that don't, basically if all the arrays has values that don't return true for this function, or if all of them have true. So that's why we put these outside of bound. And then we do while high minus low bigger than 1. So basically while we are not in this situation where, let me actually write it here. So we have false and then we have true. And we want to stop only when we reach low here and high here. This is where we want to stop, which is when the difference between the two is 1. So that's why we do this while loop. And then we calculate the mid, just normal binary search. To avoid overflow, we can use binary operations here. And now we just apply the function. What is the function? It's this, right? So if, except this is mid, if this is bigger than success, that means this is true. And since we want high to always be true, so let's say maybe either we were here or we were here for mid, then we'll just assign high to that value, right? So to shrink the search window that we are looking at. So we put mid. Otherwise it's false, and since we have the variant that low will always be pointed at false, so maybe mid was here, maybe mid found false here, and so in that case we'll put false there. Now maybe it was here or maybe it was here, but regardless we'll put low at that position, because if we put it at mid plus 1, we may end up putting low at a true value, and that's not what we want, because we have the invariant that f of low needs to be false. Okay, so now we just put low equal to mid, and now we have, when we exit this binary search, right, the value we want to use is, the index we want to use is high. So this is the index that we are looking for, is in high now, because high is the first true. When we finish binary search, the high will be at the first true, will be exactly at this position, right? And so that's what we use here. So we say pairs, we want to add it to pairs, right? So we append. Now we said when we find the index for the first one, it's with the remaining part of the array that is the number of potions we can make a successful pair using it with S, right? And so that's why we put here just the remaining part starting from index high. So to do that, we just get it this way. And then that should be it, pretty much. So if we run this, it should work. Can submit. And that passes our test cases. Now, this here is O of the length of P time, and this portion here is first the length of S multiplied by binary search here that we do on P, and so log of NP. So it's sort of this plus this is the time complexity. Now, if we want to just like classify all of them as the same variable, maybe we guarantee that they have similar bounds, then we can just use this as this, like this, and then it's just O of n log n, right? So that's the time. Now, in terms of space, we are only using the pairs extra variable, which is O of ns, the length of S. So it's sort of O of n space. Yeah, so that's pretty much it for this problem. It's a straightforward application of binary search. Please like and subscribe, and see you on the next one. Bye.